Ramanujam from Chennai Institute, and he'll speak on bounds on proof size and security verification.
Thank you very much. So, let me just see this. Yeah. Okay. So, thanks very much, and I thank the organizers for giving me this opportunity to be here and to talk to you. I'm talking about security verification, but actually specifically in the context of security protocols, but mainly on looking at some size law bounds and use it for getting bounds and verification. So the security protocols are 3-line programs that people still manage to get wrong, said Roger Needham, and I think that's the spirit of it. I'm not going to talk much about protocols, but really in cryptographic protocols, what happens, there is a core to it, and that's what we'll be talking about. So this is the so-called Dolovyov models of security protocols, where what is encryption? You have some terms and you have some key and you use it to encrypt. And decryption means that if you've got the encrypted term and you've got the inverse, you can decrypt it. And anytime you want to bundle data together, you so you can concatenate them, and when you've got pairs, you can split them. So basically a very simple term algebra, and so the important operations are pairing and encryption. And these two operators don't really interact very much with each other. But with this, you can actually build security protocols, which are sequences of messages. Like for instance, here is A is sending something to B, where the ID of A is paired with some secret number, perhaps nonce, and encrypted with the public key of B. And then, when B receives it, presumably decrypts it, extracts N, and then sends it back to with the public key of A. Now, this is the sort of thing that happens, and this is the basic cryptographic protocols in a very abstract viewpoint. Now, for instance, if you want blind signatures, sort of thing that electronic voting asks for instance, where A wants to get the B signature on some note N without actually B being able to read the contents of that note N, right? So this is the sort of thing. Now again, there are like protocols for this. For instance, the way it is done is that A picks some random number N and sends it to B, but the pair operator here, I put a square bracket, it's a slightly different kind of bundle, it's a different kind of pairing. The way it works is that if you have got both A and B, you can form the pair, but if you get the pair, you can't unbundle it. If you have one of them, you can get the other. And so what happens is, now B gets this bundle and signs it. Signing usually means that you encrypt with your private key, but magically the signature seeps through. I mean, it goes in, that's why it's called blind signature. And now if you have R, it's encrypted with the public key, and then you encrypt it again with the private key that's applying the inverse. So R gets released, but N is now signed with B's key. It's sent back to A. Now A has R, so it's one of the terms he has got, so he can pick up the other term, and therefore A receives the signed term and can use it now. This is the kind of protocols that are used. Now, what's the rule that you use in terms of inference? This blind pairing operator that we just talked about acts like a pair. If you have T1 and T2, you can form the blind pair, and if you have got one of them, you can get the other. Don't worry about the down arrow sign for now, that is for normalizing terms that we'll use. And the important point is that there is an equality here, that when you have a blind pair and you encrypt, the encryption goes through. So the encryption distributes across the blind pair. And so this is the so-called Dolovyov model, where you have some bunch of so-called synthesis rules, like for instance forming pairs, forming encryptions, or analysis rules, where you have constructed terms and you can deconstruct them. And so what you are talking about, what is called a passive intruder detection problem, basically says that if you have got a finite set of terms, can one derive a given term T from it? And it's easily seen to be decidable. Well, there is a notion of, so you have a notion of proof here, and you have a notion of normal proofs, and you show that if a term T is derivable at all, there is a normal proof of it, and you can put bound, and there is a subterm property where you show that every term that's occurring in the proof is actually a subterm of one of the given terms or the term that you are trying to derive, and from that you can get a bound on the size of the normal proofs and use it to get an algorithm. Well, okay, so what is this normal proofs? Well, non-normal proofs are where you do some extra stuff. For instance, here you take two terms, bundle it together and then split it. Of course, you don't need to do it. Another one where you encrypt it and then decrypt it and you get back T. Of course, there is a shorter proof available here. Now, so the normalization rules are generally of this form, where it tells you wherever you have got a proof where some redundancy is there, you can eliminate it. And well, as I said, the subterm property that you use, I'm not going to go into this. And in this very simple system, subterm property is something which is extremely easy to prove. And once you have got this, so normal proofs are those where you have got this subterm property and you can use it to get a polynomial time algorithm. This is the basic idea. So in general, the height of a normal proof is bounded by the number of terms you have got, and therefore you can start with a given initial set of terms and keep repeating what you can get in one step via normal proofs and then compute whether you have got your term or not. Now, in the kind of operators that I was talking about later, with this blind pairs, things are somewhat different, right? Because now, okay, so what is the term algebra that we are looking at now? Well, we are taking this basic term algebra with pairing and encryption, and you are adding this blind pair. But with blind pair comes this extra business of these equations where encryption distributes across the blind pair. Now, so we define a notion of normal terms. These are terms where where you always push encryption through as much as you can, and so that's the idea. So whenever you have got you push all encryptions all the way inside, and that's a normal term. So we work only with normal terms. So what's the inference system now? The inference system, whenever you got a blind pair and encrypt, you will push encryption inside when you have a key, since you can encrypt and you can push it inside. And in general, when you've got an encrypted term and an inverse, you can decrypt. Whenever you've got an ordinary pair, you can split. When you've got a blind pair, you can't split it. You can split it only when you have got, if you've got one of the terms, you can get the other. And the synthesis rules are very straightforward. Whenever you've got keys, you can encrypt, or you can form pairs, blind pairs. So, and so here is where, in some sense, this is the main view of security protocols that we are talking about. Many cryptographic operations, what's being done in security protocols, can be abstracted to some inference rules of this kind, and then the fact that an intruder who is watching the network, picking up terms and inferring from those terms some new terms, is captured by this inference system. So when you want to talk about capability, placing bounds on the intruder's capability, which is what you do in security verification, you are basically, you can translate that problem into analysis in this kind of inference terms. Of course, this is the so-called passive intruder who is simply collecting terms and inferring, trying to infer some knowledge. Now, how do we use this whole thing here? Now, you don't have to, so the system that I am talking about, I think the main objective of the talk is to show that this gets hard. We will show that it's in fact the term derivability problem is deterministic exponential time complete, as opposed to the polynomial time algorithm we were talking about a moment ago. So of course one can ask, do we need a system like this? We can work with a simpler system. In fact, we worked on this earlier, and now Stephanie Delon, Steve Kramer, and Mark Ryan have, expanded on this considerably, where you don't allow all arbitrary encryptions to seep through, but only particular, you take particular terms of the form encrypted with a simple key, and you allow only inverses to seep through. If you remember, in the blind signature, I get something blind from you, and oh, by the way, blind signature is something probably I should have mentioned this earlier. It's very simple. You think about it, you want to get my signature without my reading the contents, right? I mean, in the old world, what I would do is put it on a piece of paper, put a carbon paper around it, put it in an envelope, and send it to you. You sign on the envelope, right? And then because of the carbon, the signature actually comes onto the sheet. You send back the envelope to me, I tear off the carbon, and then I've got your signature on it. That's exactly the principle here. right? Now, the only thing is that allowing arbitrary terms to arbitrary encryption to get in creates problems. So, you can work with this where you work only with inverses, and then the problem is polynomial time decidable, and this is good enough for many practical purposes, I think. But the mathematical problem remains, and that is what we are talking about here. So, this system suffices for things like electronic voting. So, even though I mentioned electronic voting as the motivating example, the problem is really mathematical as far as I am concerned. But then there is a much harder system. If you allow things like cancellations, and there is a sum operator that you can define, and here for instance they have a system where if you have got two sums and if there is a common term, you can cancel it. Now, this happens for instance when you use exclusive OR as a means of encryption, right? Exclusive OR is a standard operator that is used, and that has got properties of this kind. Now, there you can show that in fact the problem is decidable, but the only upper bound known is non-elementary. We do not know whether there is an elementary upper bound at all. So, what we are talking about here, where you do not have you are not working with commutative operators and cancellation, but what you are talking about is encryption is distributive, and what we show is in fact it is DXP time complete. So, how do you do that? So, before I move on to how we do this, what about other cryptographic primitives? I mean, I am talking about a very specific one here, namely blind signatures. Now, as I said, exclusive OR is much studied, Diffie-Hellman, homomorphic encryption, blind signatures. Many of these you can abstract out into a model like this and reason, and we have contributed to this in a couple of papers as well. There is a large body of results, and but I must say that many of these, the story is nothing nice to talk about. Most of these are at least co-NP complete or exponential time complete. Well, this is now, but those are in the what I call the active intruder case. The passive intruder case typically tends to be polynomial time, and what is surprising here is that even the passive intruder problem is hard. Okay, so how do we use size lower bounds in this? So, first, because of the fact that encryption distributes across pairing, you do not have a subterm property. So, for instance, here you have got an AB pair which you encrypt with K, and then you remove B encrypted with K because you have got it already, and therefore you can get A encrypted with K. Now, A encrypted with K is not a subterm of any of the terms that you began with, right? So, now this is of course a very simple example, but you can pump it up. So, what we show is that for any n there exists a set of terms xn and a term tn such that the size of this input is order n and tn is derivable, but any proof is of size at least 2 power n. So, and I will not bore you with the details of this. Somebody is interested, I can talk about this later on, but this is basically a coding that we make use of to show that basically an n bit counter can be simulated by doing this. And the fact that what I said about blowing up, not blowing up, I am sorry, that you get new terms like A encrypted with K which were not present, which are kind of implicitly present, that is what you make use of, right. So, so let me, as I said, I will skip this proof for now, but it is there, and if somebody is interested we can talk about this later on. Okay, so basically that we can, so we need a notion of normal proofs that has to take these into account, and this is mainly the point. So when I am using terms like sequences k, k1, k2, etc., I am really just notation for talking about something encrypted with k1, then encrypted with k2, then encrypted with k1, etc. Note that these are words, and repetitions are allowed, right. I mean, when I encrypt with k1 and then with k2 and then again with k1, there is no way you can reduce it, right. You have to have the keys and go through in sequence, and that is what introduces all this mess. Okay, so once you have got that, now you can use it for getting complexity of the verification problem that we began with. Now, how do you, so as I said, just the existence of a proof, existence of a particular term such that the proof is of exponential size doesn't of course mean that the general verification problem is hard, but there is enough machinery there to make use of, and that's what we do. Now, so for the reduction for the lower bound, we the problem that we use is something which is known to be exponentially hard, and that is this idea of alternating push down systems. Now, there is the intuitive connection is really straightforward, because what you are doing is when you encrypt, you keep pushing something, right? Because as you keep longer and longer chains of encryption, you are building strings which you can access only from the other end, right? So, if I start encrypt with K1, then K2, then K3, if I want to access the inner term, first I have to get rid of K3, then K2, then K1. So, it is a kind of a last in first out that happens, right? So, this is really the heart of the matter, and you can make use of that. So, a push down system is one where you have got some control locations and some stack alphabet is given to you, and you have got transition rules of this form. This says that if the push down is in state X, now you replace the top by a string B1, B2, Bn, and this is a state that you move to. Now, this is alternating, so you have got this list here, and a standard push down system otherwise would be where you examine the top of the stack and replace it by the new string from X, let us say, to Y, right? And so this is, and now you can look at the configurations of a push down system, and that is an infinite state space, and in general, of course, it is not clear that you can do reachability at all. So, what is a configuration? A configuration is where your system is in a particular state and your stack is in some configuration in some sequence X, and now the question is, you want to know whether one configuration is reachable from another. So, what the question that in particular that we study is, I give you some target configurations C, and then I want to know whether that target, that set of configurations is actually reachable from the initial configuration. And in general, how do you rewrite? Well, in the case of not alternating the standard push down system, it is easier to see perhaps, where what you are saying is that I look at the stack configuration that I have got and see if one of the rules is applicable, and whatever is the stack configuration I have got, now the top of the stack is going to be replaced by one of the strings that in the rule that you are applying, and that gives you the new stack configuration, right. This is the basic idea, and now you keep repeating that and you talk about reachability. The problem that we are talking about is the backward reachability problem, as it is called. I don't know why it's where you are given the target and you want to know whether you can get from there. And this is a problem that has been shown to be exponential time complete. Actually, in this it's a bit in this infinite state space. Firstly, it's not even clear that the reachability problem is decidable at all. But this was proved by Buchy in 1960s, I think, that the reachability problem in fact is decidable. And if you look at the set of stack configurations that occur along, you give me any regular set, in fact, of configurations and ask, is it reachable? And you can actually show that the set of stack configurations that you have got, it's an infinite set of words, but it's a regular language, and therefore can be represented by a finite state automaton. So, and that's a very nice algorithm which has been considerably expanded on by Stefan Schoen in his thesis, and in fact in a couple of papers they have looked at the complexity of associated problems, and this is one of them in that context, and that's what we make use of. So, what we do is, given any push down system, basically we can come up with a bunch of terms and reduce the derivability problem that we have got here to that. So, in general, whenever you have got some suppose you have got a rule of this form where you replace the stack, move from control state A to B, replacing the stack top by X to Y, I can introduce a term where it's simply a combination of blind pair and encryption. Okay, these subscripts by words x1, x2, xn. I mean, in general, when I am subscripting by a word x, what I am talking about is a sequence of encryptions that I perform. Right? If the word is ABC, I am encrypting with A, then encrypting with B, then encrypting with C. That's the notation for this. So you can actually code up these kind of rules here. So basically what is happening here is that any in the push down derivation system, whatever appears on the head of the system basically is going to be something that's going to sit as the innermost term in my stacked terms here. That's really the main idea. And I need some base or a counter to keep track of where I was, and that is, so I just have that, and what the recognition of the rule will do is to release that particular term A, and to release that you have to go through all the rest, and that's exactly what you make use of. And then we can show that a configuration set of final configurations is reachable from the initial configuration if and only if from the starting term is in fact derivable, and that shows that the passive intruder problem is DXP time hard. For the upper bound, actually what we use is, well, pretty standard ideas with proof normalization, except that normalization rules are quite intuitive, but you have to be a little careful about the complexity, how we do it. Well, these again are fairly simple. For instance, in the one here, so in general, for instance, if you first encrypted two different terms, T prime and T double prime, and then formed the blind pair and then encrypted, what you are saying is you might as well encrypt and then do the blind pair, right? So you can, so basically what you are in this process, what you are doing is that you are always pushing up the encryptions in the proofs, right? You try to push up the encryptions as much as possible and push the blind pairs down. That's the heart of the normalization rules. And there is a lot more. Let me skip these. So, and then the key lemma says that with this notion of normalization, whenever there is a proof, there is a normal proof, and then some technical ones, but these are very important because that's what gives you the decision procedure. Instead of, you don't have a subterm property now, but what we can show is that, for instance, the first one says that if you have a proof, now take any subproof, within the subproof, whenever you see a term occurring in it, right, I can guess some keyword. Now what is this keyword? A sequence of encryptions, those subscripts that I was talking about. It says that then there is a subterm and some keyword X such that this is the occurring term. So it's not that every term occurring is actually occurring as a subterm, but every term occurring is occurring as some long encrypted sequence of some given subterm. What is that sequence that is there? You may have to guess, right, as far as this is concerned. Now a whole lot of remarks of this kind, and it's a bit tricky because for different set of rules the property has to be carefully analyzed. So but having got this idea of normalization, you can get an upper bound pretty much like the earlier arguments. So what we show is that every term in a normal proof is of this particular form where you take a subterm and it's a sequence of encrypted using a word which could be very long, but that word is actually got from the original terms that you began with. And then comes the very important remark which says that, well, what are the kind of words that you need to use here? Well, you would have to have an infinite collection of words, but that infinite collection of words actually forms a regular set. So even though you have to guess words and those words could be arbitrarily long and they come from an infinite set, it comes from a regular set. That's the heart of the proof, and it's a little complicated, but having got that, then what we can show is that checking whether a term is derivable or not boils down to checking whether this particular language that we have associated is empty or not. So it's emptiness checking of this particular regular language, which we can then, now this language has nice closure properties and we can make use of that to get a representation. And the representation we get is an automaton saturation construction. You build an automaton and go as follows. You start with, so well, in this particular example, whatever is the set of terms and the goal term that you start with, look at all the subterms and these are the states of your automaton, and you add transitions by looking at rules that tell you what you can do. For instance, In this case, t is in fact a subterm of with t and t prime together, I can what is the situation here? I have the blind pair t prime, and above I have the term, one of the terms t prime, and therefore I can get one of the terms. In this case, I put in transitions. The earlier one says that from t prime, when I have got k, I can get t prime encrypted with k, and so it goes on like this. But let me not go into this. This is so this basically looks at all possible one-step derivations associated with normal proofs. That's really the main idea, that they can be used to saturate the automaton. And so the automaton construction is again inspired by what Buchy did, but somewhat different. But basically, you start with the initial set of terms and one special designated term to talk about the final state, and you take the set of keys. And remember that the words that we are talking about are key sequences, and so the alphabet of the automaton is simply the set of basic keys that you begin with. And here is a bunch of rules that tell you how to do the saturation of the automaton. It is not a one-shot thing. It is an iterative construction, and you have to show that it reaches a fixed point. And so what we can show is that if ever a term is derivable, then there is a way by which this automaton will reach the final state. There is a path for it, and the converse is that whenever the automaton actually reaches the final state on a word, that the term encrypted with that word is actually derivable. So we can use all this to show that in fact the problem is solvable in exponential time, mainly because the automaton saturation procedure adds transitions, and the number of transitions that it can add is exponential, and each time the refinement step itself takes a singly exponential time, so the whole thing is 2 to the order n. So that gives you the tight bound, and let me end with so as far as what we have been doing is that for different kind of algebraic properties that you come across in operators used in cryptographic protocols, you have this term algebra, and we are looking at some extensions of the algebra and looking at an inference system associated, and the main idea is to get bounds on proof size and use it to get bounds on associated security verification. That's the heart of the procedure, and I hope I've tried to show you that this is what we do. And in general, there are not too many lower bound results on the passive intruder reduction problem, and as I said, the really interesting cases, this stuff that I talked about with atomic keys, but for encryption it's also important to work with constructed keys, but it mainly means that the operator that I define turns out to be associative, but that's really not a problem, and this is something that we can do. But what is really hard is the one that I mentioned earlier, where they use for XOR. In general, if you are working with an abelian group operator with distributive encryption, the only thing that we can get is a non-elementary upper bound, using Higman's lemma kind of arguments, and we don't have any good bounds for theories of this kind. But those are important in cryptographic applications, but we have got no results on those things. Okay, let me stop here. Thank you.
Any questions?
Can I have a commercial while the questions are on?
Go ahead.
No, this is that's for, somebody wants to.
So do I understand correctly that the purpose of this is to get automatic proofs of security of cryptographic systems?
Yeah.
Say some kind of calculus, and then you want to prove that certain properties are correct by doing it automatically.
Yes.
So your results are kind of on the negative side. You're saying that you have exponential lower bounds on the proof size, which to me say that there's no hope of actually verifying some properties of non-trivial cryptographic systems by computer. Am I right?
Yes. So there are two ways of looking at it. One is that those who build theorem provers and do this very often say, this kind of verification is not, going to be done online. It's a one-shot verification. You write the protocol, and so it doesn't matter if it, is very bad. But I don't know how to take that. Consider it as an algorithmic problem. It's clear that if you have got somebody with an online capability, right? Now, see, okay, so this can also be good news. We have to look at it the other way. Because what you're saying is that for the intruder to be able to infer a term, right? This is a passive intruder case. Right? Intruder doesn't do anything. Intruder is simply collecting terms and inferring new terms, right? And what you're saying is that now the intruder must have enormous computational ability to be able to infer, right? I mean, it cuts both ways. So you can
Assuming the intruder works by the rules.
yes, of course. So that's another big thing in this, intruder modeling and what kind of computational abilities you give to the intruder. And I didn't mention anything like guessing, right? So there is a lot of stuff to do. So this is mainly saying that the underlying cryptography, the algebraic properties there can actually impact on the algorithms that are needed for composing these. Yes, I mean, in some sense that's the.
But it also shows that it's difficult to automatize
Yes,
security
yes, yes,
verification.
yes, for sure. Thank you.